Hi everyone. So in today's video, I'm going to go over this blog from Hugging Face. I just found this very interesting. I'm working on something very similar, and yeah, I was going to read it and thought maybe I should record it and share my thoughts as I read it. So here we go. From digits to decisions: how tokenization impacts arithmetic in LLMs, and you can see the authors here. Right. So recently there has been a lot of buzz around a seemingly simple question that even soda models fail to answer, which is figure 9.9 or 9.11. So as you can, if you're familiar with that Twitter circle, this was quite trending a few weeks ago. Despite various attempts and variations of prompting techniques, most frontier models still struggle to make an accurate comparison of these two numbers. This highlights a broader issue many of today's models encounter. They have limited mathematical reasoning capabilities. While there are multiple conjecture on why this is the case, including the composition of pre-training data set and the model architecture, in this work they investigate tokenization and how it affects a model's ability to do maths. So they have a detailed approach on comparing different methods of number tokenization, why reading from right to left is sometimes better than left to right, okay, and a clear front runner of tokenization methods for arithmetic and algebra. All right, looking forward to reading this. So a brief history: back in 2019 when GPT-2 came out, it used byte pair encoding. This approach works by merging frequently occurring subwords into a single unit, right? So you'll have probably certain numbers which are more frequently occurring than others in the pre-training data set, and they'll join into becoming single tokens. So because of how this algorithm operates, the resulting vocabulary depends heavily on the training data. So this led to inconsistencies in how numbers are tokenized. So 1 to 100 years like 1945 become single tokens, while less frequently seen numbers become multiple tokens already. So in this visual, whatever is in pinkish is two tokens, and you can see something like 700 is one token, while 741 is two tokens. So 740 is one token, and 741 is two tokens. All right, interesting. 4 years later, the herd of llamas began the stampede. Llama and Llama 2 used sentence pieces byte pair encoding implementation with a no table tweak for numbers. So they split all numbers into individual digits. This meant that there were only 10 unique tokens to represent any number, simplifying numerical representation. So it didn't have anything like 1945. DeepSeek released a model much later called DeepSeek V2 with a similar single-digit tokenizer. I remember when we were working on the Pythia project, we also wanted to do this, but I think we somehow missed a tokenizer. All right. Later on, Llama 3 took a different approach and tokenized them in groups of three digits. As a result, numbers from 1 to 99 have one token each, while number of 1000 onwards are composed of these tokens. So 1000 would be 1 and triple zero as one token, I assume, or 100 and 0. Let's see. So a new paradigm, right to left tokenization. So far, tokenization process texts from left to right, which is similar to how we write English, but certain languages are indeed written the opposite way. For instance, Urdu and Arabic. For instance, if three-digit tokenizers encounter the sequence 1, 2, 3, 4, 5, it will scan from the beginning, breaking it down into segments of 1, 2, 3, and then 4, 5. Alright, so I guess that also answers my question of now how 1000 would be tokenized. So it would become 100 and 0. In right to left tokenization, you do this from the end to the beginning. In this case, 1, 2, 3, 4, 5 will become 1, 2 as one token and 3, 4, 5 as another token. Recently, there has been some exploration too of forcing this right to left tokenization behavior, which has shown to benefit certain arithmetic operations. If you think a bit about it, arithmetic operations like additions are always like you start from the last digit, the rightmost digit, and do stuff. So maybe this helps. I don't know. We'll need to see. It has also been rumored that Lord uses this. Okay, to better understand, let's see. So if you would to do left to right, you would get for 3789 plus 8971, you would get this, while for right to left, you would get this. In the three-digit example, 9 plus 1 should map to 0, but and ends up grouped together with 8 to form 80. Since the first three tokens 1 to 5 are already grouped together, this shift in the tokenization boundary process additional complexity in the learning process, which has shown to be detrimental. In the right to left thing, each digit of 580 aligns neatly with its corresponding suboperands 789 and 791, which is intuitively a more intuitive grouping. Hmm. I don't know why this happens. So is this an example of so why did 9 plus 1 become 80? 9 plus 1 should map to 0, right? But ends up grouped together with 8 to form 80. Okay. What they're trying to say is if you add these two numbers, you get 12580. But if you look at the tokenization of 12580 in a left to right scheme, you will get 125 as one token and 80 as another token. While if you do the right to left scheme, you'll get 580 as one token, which maps cleanly with 789 plus 791. I assume it's 1580. Yeah. Okay. This makes sense. This insight suggests that the three-digit right to left tokenization could potentially be improved on the standard left to right. Okay. So how numbers are tokenized? In GPT-2, you have pure BPE with no special cases. For Llama, you have everything as a single digit. For Llama 3, you have 1 to 999 as unique tokens. And then Lord seems to do this right to left, but in a three-digit way. Okay. So let's create a fair comparison of different methods. The goal of this investigation is to compare these tokenizers and the different ways of processing numbers in a way that minimizes the influence of external factors like architecture and everything. All right, because you can't really compare a GPT model's learned tokens to today's Llama model because GPT-2 models were much slower and saw much less data and much lower quality data. All right, for experimental setup, they took three tokenizers. Oh, I think I missed this paragraph. Thus, one important design decision is to evaluate models trained from scratch. All right, same data mixture, training configs, and roughly equal compute budget, which is the number of model parameters and training tokens. The only meaningful difference is the tokenizer used. Okay, so they have three tokenizers: GPT-2's, BP, Llama 3's three digit, and DeepSeek single digit. For the right to left, they create right to left version of the pure BP and three digit, where numbers would be chunked into groups of three. For single digit, it reduces the same thing, so it doesn't make sense to create another one. Okay. To achieve this, we add an extra pre-processing step which forces right to left behavior when producing additional tokens during inference. So what are they doing? So this is loading a tokenizer and then they add an extra step to the pre-tokenizer. So you're doing right to left, all right. And then this is what Llama already has. Okay. And now if you split it 42069, you get 42 and 069. I'm not a huge fan. I would have liked 420 and 69, but just kidding. So for the model config, you can now train using the original Llama, but since different models have different number of tokens, you need to modify the hidden layer so that the model has roughly similar number of parameters. All right, because you have one embedding dimension per vocabulary token. So if model A has 32 parameters, model A has less number of vocab size, then you have less number of parameters. So for a fixed number of training tokens, model B learns more due to its larger embedding matrix. And to do this, they reduce the number of hidden layers in models with larger vocabularies. Okay, makes sense. I am not a huge fan of this. I would have liked if they did something else. First of all, they could have kept the same embedding dimension, sorry, the same number of tokens, and then padded some tokenizers and left a few others. Yeah, this just seems a bit wrong, but let's see. For the pre-training mission, they use FindWeb, WebMath, OpenWebMath, and Profile. Okay, so they use web data, math, and code. The relative weights are based on token count. So in total, they have 120 billion tokens. Alright, so for evaluation, it is important to note that LLM's training process is non-deterministic. Even after controlling everything, you can have noise, right? To account for this, we train three additional models at the token with the tokenizer that produce the highest variation model scores. on the same data mixture using different seeds. For each task, we take the standard deviation and assume that this value is the upper bound of variability. All right. So with a three-digit left to right model, the highest variation. So you take the model with the highest standard deviation. Okay. Train same model with different random seeds. Okay. For each task, evaluate. Calculate task specific standard deviation. So for task A, we report 0.034 as the standard deviation for all models. Okay, and then similarly for everything else. Okay, understood. We divide our evaluation suite into two main categories. So you have word-based problems, where you have, I guess, word math problems, and then for simple arithmetic problems, where you have plus, minus, multiply, divide. Okay, the difficulty of the problem, harder problem has more decimals and more digits. Float into operation based splits. Okay, whether or not to use commas, the arithmetic operator used in the problem. Given the relatively fixed form answers in the evaluation task above, the evaluation metric is quasi-match, okay, quasi-exact match. So with normalization to account for minor differences. So 127.60 and 127.6 should be an exact match. And this comma thing should also be an exact match. Okay, makes sense. So let's look at the results. So when you're doing one digit and come to task is number of digits. So I assume, okay, no, I think this is, yeah, if you're doing pure BP operations on one digit, then even then right to left and single digit are better. But even more so, single digit seems to work better in cases where nothing else works as well. hmm And then it's close by in the one case, it's a bit worse. Okay. Based on operations as well, I think add, divide, multiply. Okay. It seems that single digit is better. And similarly with number type. So with the differences for easier problems are less pronounced as the complexity increases. There's increasing gap. So best performer is still single digit. This suggests that single digit tokenization more robust. Additionally, while it's intuitive to assume that integer problems will have better performance, which is also confirmed by the results, we also found a performance gap between floats and integers is similar across all tokenizers. So there doesn't seem to be any inherent token. All right. Mhm. This makes sense. We found that a model trained on right to left tokenized data results in mostly significant improvements when compared to a left to right tokenized data. Okay, this shows that in the optimal setting for arithmetic operation compared to the typical left to right. So if you look at right to left, it's a bit better in addition. Um, what? I don't think this holds. So they say that right to left tokenized data model results in most significant improvements when compared to training on the left to right tokenized data. So for the left to right, addition is worse, but divide is better. Multiply is close enough, subtract is worse. Pure BP tokenized show inconsistent performance when numbers are chunked in group of three from right to left. Okay, I think this is the plot they were talking about. I looked at the wrong plot. Yeah, this is a plot for this subheading. Okay, evidently, pure BPE based tokenized without any additional number processing don't benefit much from right to left tokenization. A possible explanation of why this might be the case is the lack of structure. Unlike the three-digit tokenizer, due to the peculiarities of pure BPE, there are some numbers that are also grouped less consistently. This inconsistency determines the advantage of right to left, which we have shown to work best when numbers are uniformly tokenized in three-digit chunks. Okay, and if you look at word problems, while the performance gap is less pronounced, we see that single digit and three digit seem to outperform. Okay, and then while the performance gap, okay, for inference, one how can you use a different tokenization scheme and see if it still does good inference? So I took Llama 38B and use the same code to modify okay the tokenizer. One important thing is When adding two numbers in a three-digit tokenization scheme, the result can sometimes produce more tokens than input numbers. So if you add 999 and 111, these are one token each, but you get 1110, which has two tokens. So they wanted to explore how much of a difference this makes. Okay. So we refer to addition that result in an extra, okay, the carry and non-carry. I think the carry and non-carry names are not the best names since addition also has a notion of carry. But okay, uh, I see. So this is the plot. Left to right without carry is orange, and right to left without carry is green. Let's just add everything. So when you add a carry, hmm, the best seems to be right to left without carry. Carry makes it difficult. For non-carry addition, digits are that are multiples of 3 produce the exact same result given the number like 528, 491 have same tokens. We see interesting cyclic trends for for L2R and R2L carry. For multiples of 3, L2R slightly outperforms R12, right? But in the next digit, R12 performance shoots up. Hmm. We found that models output tokens perfectly formatted as R12 with just a few R12 examples, despite being trained on our L2R. This is interesting. So these models are not just but also learning the distribution. When averaging across all digit lengths, there was approximately a 10% improvement. What should you use? While byte pair encoding is popular, there should be pre-processing steps, right? If you want to use a tokenizer that is numbers for digit up to 3, then you should use right to left. If you want to have a trained model where the data was L2R, you can get better math performance by running inference R2L, and then word problems are less apparent, but we found single digit and three digit to outperform. All right. Okay, this is a very good blog. I had this question and I now have an answer to my question. So, yep, feel free to check this out. I'll have a link in the description and thank you for tuning in. See you guys soon.